So patterns and designs. How about that? So we're talking about the E field and the H field a little bit. Gain as a function of the radiation pattern, and a little bit on antenna modeling. Has anybody here done modeling?
I have, but
Any
not
neck?
long. I did eons ago, and then I decided, let's just build.
Trial and error. Trial and error, Swimmer.
Yeah.
I built a it's a type dipole, but it has a matching section where you
C5R or 400 ohm needles coming down.
it's a little bit like that, except it's a little bit wider, probably 600 ohms.
Okay.
And then you go out, and they actually put a little feathers at the end, and maybe about a quarter of the way from the end to broadband it a little bit. It was MERS antenna. I recalculated it for 2 meters. And,
Okay.
I think called the hog fence antenna is one name for it if you look for it.
Or the little feathers, capacitive hats.
They would act, I would imagine, capacitively. Okay.
Because those are still kind of a mystery to me, and we'll talk about them.
Yeah. Yeah. So you should. Oh, I'll just throw on your.
Okay, so we say that directional antennas have gain, but it's only relative to the direction that the antenna is pointing relative to where it's not pointing. Like in the case of a beam antenna, you've got more power coming out in one direction than you do on the sides and the rear. So they measure the gain as the relative field strength or power from the forward versus the side or the rear.
It's versus so isotropic or a dipole, not forward or rear. That's another measurement.
When we're talking about pattern, it's relative to side or rear.
Right. Not gain.
Okay.
This thing was actually a variation of an extended set, which is 5/8 wavelength
Yeah.
instead of half, and that's why they did that funky little matching.
The
Okay.
front to back ratio is the one that's you were thinking of. That's the rear.
All right. But the bottom line is power out equals power in, or vice versa. And in the real world, power out is less than power in.
Always.
So they say the total amount of radiation emitted by a directional gain antenna is the same as the total amount of radiation emitted from an isotropic antenna, because you got the same amount of power regardless of what kind of antenna it is. So how does the total amount of radiation emitted by a directional gain antenna compare with the total amount of radiation emitted from a theoretical isotropic antenna, assuming each is driven by the same amount of power?
Charlie.
Okay. So I guess what the manufacturer actually does is set up some sort of test and go measure field strength to come up with these patterns. Or they do a neck simulation and say, this is what it does.
These are
might be that one time.
These are near field, right?
No, far field.
These are-
Near field is indeterminate. Which is why you never say anything about it, because there's too many things that affect it. And,
Unless you're Dave, Pirate Dave, to use your or.
Yeah.
Is there a definition for far field? Like, where is it?
we
It's it's a wavelength. I forget how many wavelengths.
I think it's coming up. I think they define it as when you're far enough away that this is basically a stable pattern. Where it doesn't change with distance. When you're close, the pattern change, the closer you get to the antenna, the more the pattern changes. And at a certain point, and if it's like that, it'll look like that
You'll
at
get consistent
100
reading-
feet or
you'll get
1,000
consistent
feet.
Reading
And
in
then
the 360.
when I was in the service, we were raising our antennas on the ship. We did it from about 6 miles away from the receiving site. They just did circles out there. And then we kept transmitting our heading, so they were recording all the information at the other end,
Huh.
which put on antenna we were dealing with.
Did you go out on the little boat and circle?
No, we were on the big boat.
No, but I mean to go measure it.
No, they had a fixed station from the shore,
Yeah.
and we were like 6 miles away doing circles,
Oh, you do a circle. Okay.
just sitting
Yeah.
there turning around. And they
Did
were
you
measuring
drink
the
more
antennas.
coffee then you do now? Did you drink more coffee then you do now?
He was the chief petty officer, that's a requirement.
Yeah, that's what I'm thinking.
Okay.
Okay. Anyway,
Michael has a question.
Michael has a question.
Pop-up means?
I don't know. Michael,
Yes, sir.
did you have a question?
Yes, I do.
Okay.
So we've been talking mostly about the radiated pattern of the antennas, implying it's, your transmitted power and everything. Is it kind of go along with it that the receive signal is going to be, you get better receive out at the directional lobe than you do at the sides or the back, say on a beam or something like that? So,
Yes.
if you set it up for a good transmission, you ought to have a good receive as well.
Right.
Okay. I thought maybe true, but I wasn't sure.
Everybody's shaking their head. Must be true. I mean, it would seem to, huh?
There are exceptions.
Well, there's exceptions to everything.
Yeah.
What are the exceptions
Where you're using multiple antennas for receiving.
for phased array?
For phase arrays.
But why wouldn't that be the same for receive or transmit?
Because it's very hard to transmit with phased arrays than a normal transmitter for hand, because you have to have multiple transmit antennas and be able to
Phase them.
phase them. I don't think anybody's doing that
Uh,
except commercial.
okay. Because we'll talk about that in a bit
Okay.
with some phased arrays. It's on the test.
Oh, I didn't know that.
And it's confusing because it's two quarter wave dipoles, quarter wave apart, fed in phase, fed out of phase, and then half, if I remember right.
Yeah.
And the other one's fade 90 degrees.
But you have, like MFJ sells a device
Yes.
where you can use multiple receive antennas
Uh-huh.
and then you can phase them. And when you transmit, you're only transmitting on one antenna, and then it receives using both antennas. And you use the second antenna to null out an adjoining station coming from another.
Yes. But that doesn't mean you can't do it on transmit. Their box isn't set up.
Do it on transmit.
You can.
Yeah.
Worked for Collins for 40 years, so obviously Rav they have a huge phased array
Right.
that they transmit and receive on, so it's what they call comm central, so that they did it back in the day, health and
That's-
welfare messages from
Yeah.
overseas. So it's a fun thing to look at, it's a huge array. Just
Oh, yeah.
takes our basic maker.
Oh, they're
So they had,
amazing.
3 different antenna systems, one in Richardson, Texas, one out in California, one in Cedar Rapids, and they could figure out which, who they were trying to reach, what propagation from what position. What they wanted.
I think you used to have one there in West Virginia, in the quiet zone where you can't transmit or anything. It changed over and it had a huge array of vertical antennas all the way around and then big phasing units. And it was just a strictly receiving site.
Yeah. So now we're jumping ahead, but what they did is.
That was
they-
back in the 60s.
We'll see the 0 degree phase, 90 degrees and 180. They were able to vary that. So
Yeah.
They could shift the directability almost like a beam. So
Yeah.
the phase they operate like a beam.
I got to kind of work on a Russian radar system they called flap lid. It was about a 6 or 8 foot diameter disc mounted on the back of a truck that they could elevate and rotate. It had 1,024 dipoles that were all phased analog. They did it with diodes changing the bias of the, and it was transmit and receive. I don't remember how much power, but it was, and that was
Couple years ago.
35 years ago.
Oh,
Not
that's
telling what-
basically what they're doing with the Starlink to make it, do 5G stuff to the phone is, same thing you're talking about, a giant array of 1,000.
Of course, these things are only this big.
Yeah.
Okay, what do we got? Oh, I keep getting my emails showing up. I guess I could turn my email off. Too late. Okay, so this is a typical azimuth, what they call the azimuth pattern, as opposed to the elevation pattern. So when they go measure the antenna, you'll get something with a beam antenna, it will look something like this. If it was a half wave dipole, you'd see lobes on either side, and they wouldn't be as directional, they'd be rounded. Okay, and this is showing the far field pattern, and their definition is it's a region where the shape of the pattern doesn't change relative to the distance. So I don't know how far out that has to be. I guess they do it by measurement, and when they get consistent patterns, I guess that's called the far field. I don't have any idea what it is for a real antenna. So what is the far field of an antenna?
Cal.
I'm thinking of delta.
Doggy.
Doggy sounds good. All right. Beam width is the other characteristic that you get out of these patterns. And they define it as the 3 dB point, where the gain is 3 dB down from the peak. So if you look at that chart, and I've tried to indicate it with that arrow, there are examples, and this is the same ones that'll show up on the exam, are kind of sucky as far as figuring out exactly where it is.
They're very vague.
Yeah, you have to believe them that that's 25 degrees. But most of the answers are far enough apart that you can guesstimate pretty well. There's one though
Back lobe, really hard to see.
where it's
Front to back
they gave you two 12 and 14.
Yeah.
That one's iffy.
You just have to know that one because you can't like a chart.
Okay, so in the pattern shown, what's the beam width? I didn't put an arrow on this
50
one.
degrees.
Our front to back ratio is a measure of how directional the antenna is in the forward reverse direction. So the higher it is, basically the more power you have going in the direction you want. Where the reverse lobe is power that is basically going in the opposite direction, which you really want to minimize. Unfortunately, like most things, minimizing that affects other things. So, we tend to make the beam wider, perhaps, if you brought it in more. So it's a trade-off between things.
But one nice thing about the front to back ratio, it blocks out signals coming from the other direction, so you don't have much noise. That is what's good about a hex beam. It's pretty wide in the front, but it's quiet the rest of the way around.
Good point. It's not just about
It's not.
focusing your transmit
It
power,
doesn't, it helps the transmit by
Minimize it.
dB, but it really quiets it down.
adjacent interference and stuff, that might be
Yes.
coming from the opposite direction, yeah.
Well, that's why when they talk about, and it comes up later, the direction finding, one of the ones they use is to generate a cardioid pattern. So the null on the rear, I mean, it's a null on the
Right.
reverse direction,
Yes.
and you can actually use the null
It's
more
better.
better than the other one. Okay, so they normally do these charts so that your maximum power is set at 0 dB on the circle, and then you have negative dBs on the inner circles, which allows you to do the comparison. So in this case, the reverse lobe is, according to them, 18, but all you know is it's somewhere between 12 and 24, and it's not linear. So I take their word it's 18. If they had a better chart, it might show up. That's what you get.
Yeah, well, what's from minus 12 to 24 was linear, looks like it's halfway through there, so half of 12 is 6 is 18.
Yeah.
Let's do it.
So what is the front to back ratio?
Billy.
Yes, Bravo. All right, front to side is also an issue because as you play with these things, the spacing of the elements and the length of directors, like on a Yagi, it affects the rear and the side. And you do it the same way. You find out, where it is in between those. And this one is the 14. So if the other was 18, I believe him that was 14. Imagine that. It's the same question. Everybody agree on 14? Now, we also not only need azimuth, you need to know elevation. So it's a little bit different plot. And you'll see, depending on the height of the antenna, as it gets higher, you get a lower elevation for the main lobe, but you get more of these upper lobes the higher you go.
That was the opposite direction.
No. When it's down, you get the
Skyway.
more omnidirectional big lobe, and your elevation pattern is maybe 45 degrees.
Okay.
And you go higher, you start to get these.
Fingers.
Yeah. I don't know if I put a picture of one of those in there. Okay. But in this case, you're looking at the largest lobe, which turns out to be usually the lowest one. And in this case, they're saying 7.5 degrees. It's approximately that. I would say it's 8.
How can you tell?
Because it's not exactly in the middle.
Round up, right?
What type of antenna pattern is shown in figure 9.2?
Alpha.
Billy.
Elevation. And that's when it's over real ground. It makes a difference depending on what kind of ground it is. And that's one of the things you do in the simulator is you can select whether it's free space, which gives you nice charts, but they're not real. Or you can pick different types of ground. And I think they might even let you do salt water.
So Bob, could you go back to the previous one and point and touch the 7.5?
Okay. Well, see, 0, 15, 30. So it's halfway between 0 and 15.
Okay, I see. I got you. Okay.
Approximately,
Okay, I see it.
Okay. And if you look at the possible answers, I mean, the next closest one's 25. So, that would be the second lobe.
Mhm.
Be about 25. So what is the front to back ratio
This is the one.
when we're doing verticals?
Look at the
Yeah,
largest forward lobe and then the lobe that's behind it, or
so it's somewhere
30 something.
looked like
Yeah.
it's over 30, but I
Yeah.
think the answer to
a
that.
little less than minus 30. So
Yeah, that's a curve.
28. Yeah, 28. 28.
Well, if you look at it.
Bob,
could
could you point this one out again? I had trouble with this one, real trouble with this one. We're taking the main lobe, the biggest
the
lobe,
main
right? And
lobe,
then looking at,
okay. But the main lobe is 0. Okay.
right,
It's on the 0 dB scale
right.
coming out this way. Okay, so that's 0 dB. When you go to the reverse, okay, you're on this circle would be minus 30, so it's not quite minus 30. And the next one's 20. So you kind of have to believe them that it's 28. And
Technically,
So I was, if you look at the horizontal axis, that's what in other words, when you go on the other side of the 90, how does that number go? It doesn't go to minus 50, right? It starts over again.
oh, well, look at these circles. Okay.
Mhm.
The outer one is 0 all the way around.
Right. Okay.
So this is 0
Mhm.
over here.
So they're saying the second lobe up is the one we're concerned with.
Oh, I see. It goes all the way. That's right. I see it now. It
Well,
goes all
I
the way.
can't tell the difference between this one and this one.
0.
15 or
No,
That's right.
This is 30. This is 30. So it's not quite 30. It's more than 20. So it's somewhere between 20 and 30.
yeah, all the three lobes are almost the same.
Yeah.
Yeah.
I see.
Actually,
'Cause that
this
line
one, I
goes all the
think-
way over. Okay.
This one I think is probably less than these two,
I can see.
but
So you're not considering your center line is 0 and then you're adding more to dBs going left.
It's a bunch, so you don't worry about it.
yeah. The very center would be infinite.
Yeah, as you go out to the left, it's the same. It
It's the
goes
same. I see it. Okay.
40, 30, 20, 15, 0.
All right. Are you straight there, Jesse?
Fine.
I see what he was looking at. If you look at the 0 lobe and you go all the way back to the back side of that pattern, it looks like it's going to be a whole lot more than 40 dB because you're in theory measuring that, but you really have to go around to the other
Right.
side.
You got to go by the circles.
Yeah.
Yeah.
So where it says
Yeah, it's a-
80, you go back the other way.
It's somewhat confusing plot. Maybe they did it on purpose. But just remember, it's 28 if you get that question.
One you can hardly see the lobe is 28.
Yeah. Okay, so antenna modeling. Okay. We can generate SWR plots versus frequency. You can do the polar plots for the far field elevation and azimuth, like the ones we looked at. And it will tell you the gain at different frequencies. They're fairly simple to use. It's kind of fun to play with them. I don't know. I think if you designed an antenna and modeled it that way and then went and built it, you'd probably do a lot of adjusting.
So what are some common modeling software?
Easy Neck 5.
Easy
well,
Neck 5?
Yeah, it's a free I can't remember the guy's name. NEC is numerical electromagnetic computation or something like that. It was done by Lawrence Livermore Laboratory,
Yeah.
all in Fortran years ago. And this other guy developed a front end or interface to it, make it easier to use. And a number of years ago, he put it out. They used to sell it. He quit doing that, so he offered his latest version for free. It uses the old NEC 2 engine. If you want to upgrade it to the NEC 5 engine, it costs a couple $100 to Livermore Lab to get. And as far as I can tell, the only thing that buys you is with the ground effects and stuff like that. You can do more of those things to simulate real ground. Other than that, there's not a lot of difference I could tell. So I didn't spend the extra money. I can play with the free one, and although there's a learning curve, I mean, it's not real intuitive.
No, it's not.
But after you get the hang of it, it's fairly easy. And there are some tools in there that you can generate radials and stuff like that. Fairly easy.
Hard to put a dipole.
The first time would be a challenge, yes. And what they do is they use this thing called method of moments, and they break up the elements into small sections and model each section and then kind of piece them together. So it's like a piecewise linear thing. One of the things you have to watch out for is, I mean, the more segments, the better, obviously. I mean, if you had an infinite number, I mean, it's like integrating the thing. Well, that takes more processing power, so it could take hours to do the simulation. If you don't have enough segments, then you get incorrect answers.
But can you pick the size of the segment? So to speak?
Yeah.
Yeah.
Yeah. When you, for each element, one of the inputs is how many segments. And normally you want to do it odd. It kind of depends, but because it doesn't allow you to place like your feed point and traps, things like that, exactly where you want. You say it's so many percent from one end or the other end of that segment. Okay. So basically it's thing to remember is method of moments analysis. And they do the current essentially for each little element. So one of the things that will show you is what the current pattern is on the elements. And if you do a dipole, you see this nice thing from 0, 0. And maximum current is in the middle, in theory. What type of computer program technique is commonly used for modeling antennas?
Baker.
That's also a mechanical engineering thing too. Doing method of moments. What is the principle of a method of moments analysis?
Alpha.
Okay. All right, the more segments, the more accurate. Too many segments takes forever to run. So you kind of do a little trial and error and figure out how many you can put in there and still have a reasonable amount of,
Still get an answer that.
yeah. Well, it depends on your computer, but it runs pretty fast on my laptop. Obviously too few, so they recommend at least 10 segments per wavelength.
Didn't the EasyNIC limit you to like 20 or something?
No,
No.
not the current one. Hadn't really found any real limits on it.
Okay.
There's also a couple, besides the regular EasyNIC, there's a couple other variations of the graphical interface. It's still the same compute engine. There's another one I played with a little bit, and it's maybe a little easier to use. I'm not sure because I hadn't done it enough. It's more graphical input. The other one, you put numbers. It's like filling in a spreadsheet.
So Bob, for understanding, in other words, if I was modeling a dipole in there, what would be the segments? A simple dipole, what would be the segments in there? Going left and right of the middle, or what would that? What would that?
What you would do is you define two elements, and you give it the starting location in XYZ coordinates and the ending in XYZ coordinates. And that would be number one, for instance. You do the second one. You tell it for each one of those, you tell it how many segments for that element. And it's just a number, 10, 12, 50, whatever. You also tell it things like the wire size, and you can pick, like, if you're using 12 gauge wire, or you got a specific diameter for, like, if you're doing a Yagi, the diameter of the rods or the elements. You can put all that stuff in. There's some other parameters. You can do the dielectric and stuff like that. But basically, you just pick the number of segments for each of those wires that you define, and then you would connect it with your feed point there in the middle. And you can specify what that impedance is. And they give you an alternate. So one of the things you do when you run it and you get a plot and you see your SWR, you can pick the alternate one. So say you did it initially at 50 and you pick your alternate at 75, you can just switch back and forth and see the difference between the two, which is kind of nice. So what's the disadvantage of too few segments?
Charlie.
That's a quickie. All these are short.